All right. It's kind of loud. Guess it's working though. Yeah. All right, I will. Oh, it's not quite time to start yet. My bad. Oh, yes, it is. All right, let me put this silliness away. There we go. All right. Let me. I'll begin with a scripture. So here we go. I'm going to start now. So this is Hebrews chapter 1, verse 3. It goes as follows. And he is the radiance of his glory and the exact representation of his nature, and upholds all things by the word of his power. When he had made purification of sins, he sat down at the right hand of the Majesty on high, having become as much better than angels, as he has inherited a more excellent name than they. So this is the start of Hebrews. It's talking about Jesus and his preeminence, the fact that he upholds and sustains the world. It's the God we serve. Well, I hope you serve that God. But anyway, I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day again. I thank you for this class and for your creation. Just help us to study it today and just learn a little bit more about motion, Lord. In your name I pray, Lord Jesus. Amen. If you missed the top hat, all is not lost. It really doesn't matter. You'll have a chance, like next class, to top hat again. I actually keep attendance by the, that sheet that's going around. So make sure you sign that. All right. So let me get started here. So today we're talking about motion. In particular, I need to talk to you guys about kinematics, really. So what is kinematics? Kinematics is the study of motion, right? And so the principal variables we use to do this are position, velocity, and acceleration. All right? These are all functions of time, and they describe something about the motion of a material object. So let's start with position. So definition, we say R of t is the position at time t. This is really just a notation, but that's the starting thing. Now, depending on what kind of thing we're talking about, let's just keep it three-dimensional for a bit, all right? So here, R of t, well, we can drop back to two or one dimensions later. Let's stick with three dimensions to start with. So the position, you need x as a function of time, y as a function of time, and z as a function of time, right? This describes the position of some object. Now, we can also talk about an event. What's an event? An event is a time and a place. So if you have a particular time and an object involved, so if you know a time and a place, in other words, if you know a time and a position, then that's an event, all right? So event is a time and a place. So if we had a pair of events, that would look something like, maybe like T1 and R of T1, and T2 and R of T2. All right, this would be two different times, two different places possibly. All right, so those are two events. If you have two events, then you can talk about the displacement between the events, right? Like we can talk about the displacement. Or delta R would be like R of t2 minus r of t1. This would be the displacement between the two events. Now, you can also just talk about displacement between 2 points in space without regard to their time. All right, like I could talk about the displacement, from this chair to like, let's see here, the gentleman with the red cap, right there. Yeah, you know who you are. There's only one of you. I was going to say MAGA, but it's not really that. But anyway, it's fun to think it was. So the displacement from here to there, like I could talk about that independent of time, right? There's a displacement. If you have two positions, we can talk about the change, going from one to the other. That's a displacement. Let me draw a picture. So, if the object we're talking about travels some kind of path like that, let's say, here's my x, here's my y, here's my z, right? Then the so-called trajectory, a trajectory of a path, is just an assignment of a position at each time along some collection of time. So that's a trajectory. A trajectory is an assignment, right? So it's a trajectory. Basically, t maps to r of t, right? Trajectory. So if we have a particular trajectory, we can talk about the displacement between two different times in the trajectory, right? Like, let me picture it. So perhaps this r of t maybe is r of t1, right? And then I can talk about another position at a later time, perhaps r of t2, like so, right? And then what's the displacement between those two events? What's that look like? It's like this guy right here, right? So the displacement would be r of t2 minus r of t1. Like that. That's the displacement between those two times. All right? Furthermore, what's a duration? What's a duration? A duration is some time progressing, right? It's an interval of time. So you might have a delta t, which would be t2 minus t1. So duration is a difference in time. It's time passing, right? So if you have some sort of absolute clock, in fact, all of this is done with respect to an absolute clock, as if such a thing exists. That's a fundamental base assumption of Newtonian mechanics, is that there is such a thing as time, and that we can all measure it without disagreement. It turns out that's not quite true. But anyway, for our purposes now, we're going to assume it's true, that there is such a thing as time and that it's universal. This is a Newtonian assumption. And as long as we have that, we can talk about the duration. And if we have a displacement and we have a duration, then we can talk about the so-called average velocity. So the average velocity would be the displacement over the duration. All right? And of course, this begs like a lot of questions, right? For example, how long should the duration be to measure the velocity? Should it be 1 second? Should it be 2 seconds? Should it be 5 minutes, right? Let me give you a real world example. I'm going home after a hard day's work here, right? And let's say it's 10 miles for the sake of discussion, right? And it takes me, let's say 10 minutes to get home. What's my average speed? What is that? Mile a minute, also known as 60 miles an hour, right? So when the officer stops me and says, "Sir, you were going 90 in the 60," and I say, "No, sir, I'm about to get home. It's only taken me 10 minutes and I've gone 10 miles. My average velocity was 60 miles per hour." He's not going to care, right? The fact that I was going 90 miles per hour over that 1 second that he measured my speed with his evil laser radar thing. I'm sorry, we should respect authority. Romans 13, blah, 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 blah. But I will pay my fine. That's the cost of going a reasonable speed. But Anyway, don't go 90 into 60. I'm just joking, of course. Although I know a guy. Anyway, so actually not a joke, but anyway, yes. Is this lecture recording? I hope so. Yeah. Oh, I mean.
Or not even just that. It just made me think.
Oh, I think I'll be okay. Anyway. Yeah, so I mean, I certainly hope it's recording. So this is average velocity. Obviously, this begs the question, average over what time, right? So average velocity is necessarily an ad hoc thing, right? What the police are measuring is not average velocity. It is what? Instantaneous velocity, right? So the instantaneous velocity is defined to be the limit as delta t goes to 0. The limit as the duration goes to 0 of the displacement over the duration, right? And you guys have had calculus, so let us dispense with this limit immediately. This is the derivative of the position with respect to time. All right? That's the instantaneous velocity. Let us be clear. Definition. Velocity is equal to dr dt. As a vector, this is dx dt, dy dt, dz dt. When we talk about velocity in here, we are talking about the instantaneous velocity. All right, if I'm going to talk about average velocity, I will say the words average velocity. Otherwise, it is instantaneous. That is understood. I will not belabor this point. There is only velocity, and it is instantaneous. Okay. Thank you to Newton for his calculus, right? So once you have velocity, you can also talk about speed. What's speed? Speed is equal to v. All right? Now there is some ambiguity, unfortunately, when we're in one-dimensional problems. We'll have to deal with that. All right? But it's certainly in two- and three-dimensional problems. There's no ambiguity here. It is the magnitude of the velocity. So this is straight up the square root of dx dt squared plus dy dt squared plus dz dt squared. This is the speed. In calculus 3, we can prove that this is also equal to the infinitesimal change in the arc length with respect to time. Arc length also has a name, all right? So like if I pick a particular base point on my, on my curve like this, oops, I'll try again. Give me a second here. So here's my handy dandy trajectory, which always kind of looks like that for some reason, just my preference. And suppose we base this curve, it's based. The curve is based. It starts here. Did I mention we look at based curves in here? All right, I'll stop. I'm not going to make a Nikki Haley joke. Let's see here. So this distance right here, this distance traveled, all right, was what we call s of t. And the formula for that is actually literally the integral of the speed as a function of, let's say, time tau, d tau, from, let's say, t naught to time t. All right, so this right here, this point right here would be r of t. The length of that curve, you can prove it's the integral of the speed over the relevant duration of time. All right? And so fundamental theorem of calculus part 1 says that if you differentiate an integral with a variable bound, what do you get? You get back the integrand, right? So FTC1 says that if I differentiate the distance traveled formula, I get this right here. All right? Another way to look at this is that, I mean, you can look at it infinitesimally if you like. So we could kind of like zoom in, look at like a little, let me not get into the Calc 3. No, it's enough. That's enough for here. So distance traveled is the arc length, right? It's actually, if you were to lay a string like along the trajectory, how long would that string be? That's arc length, right? Arc length is distance traveled. Yep.
This is a little bit not with this, but just in general, I remember at the beginning of the semester you saying that you should watch like the lectures and the previous like your notes and everything like that.
Uh-huh.
When it comes to when you just were like talking, it's like, oh, it's like Calc 3. Is that something that we're just gonna have to like find out on like the lecture notes from the past year?
Well, if I'm talking about it in here, it's physics. My point is to go into further detail, it would be calculus 3. Yeah, that's all. But, I mean, in calculus 3, we'd spend like 30 minutes on that, you know, the deep background stuff. But listen, let me give you guys an example. So let's see here. Example 1, something pretty simple, right? If we had, this is our position, something like R of t is, oh, I don't know, we'll do something really nice. R cosine omega t, R sine omega t, and then let's say z naught, all right? So this is a position as a function of time, all right? So we can calculate its velocity, and we can calculate its speed, and we can even calculate its acceleration, although I haven't defined that yet, right? So what's the velocity? dr dt. And so that's minus r omega sine omega t. And then r omega cosine omega t. Now what am I assuming about omega here? I'm assuming it's, well, I guess it's not, it could be 0, I suppose, but that would be boring. But let's assume it's non-zero just for the sake of discussion. It's a constant, all right? So if it was variable, if it was a function of time, when I differentiate, I would be obligated to do a chain rule and multiply by d omega dt as well, right? So I'm assuming omega is a constant here. So that's the velocity. The velocity is a vector, all right? Yep.
So, in this situation, the object would be moving in a two-dimensional plane. It would be staying constant in the z-axis.
Yeah, that's true. Uh-huh. Yeah. We could picture it. It's staying in the z equals z naught plane. That's true. Very true. Let's see here. What's the speed for this one? So the speed is the magnitude of the velocity, and that would be the square root of minus r omega sine omega t squared plus r omega cosine omega t squared. And what's that? Well, notice that sine, yes, sir?
What is the significance of omega here?
Omega is a constant, a dimensional constant. It describes the angular velocity of the object, but it's just a constant. I mean, if you want me to spoil it, I can tell you this is a circular motion, and like that basically describes how fast it's going around the circle. If omega is bigger, it's going faster in the circular sense. Okay, anyway, so here, what's the speed? Well, sine squared plus cosine squared is what? 1. But you've got a r squared omega squared as well, right? So this simplifies back down to r squared omega squared, and let us suppose that r and omega are positive, so we're just going to get r omega. So this is actually an example of a trajectory which has constant speed. This is a constant speed path. And so we have constant speed. V equals to r omega. And so I can calculate the distance, right? What's the distance traveled? So what is that? That begs the question, right? How do you know what's the distance traveled? What do you have to know to start with if you ask a question like that? You got to know when you started, right? So what do you guys want to, you want to calculate the distance traveled, let's say since time 0? Would that be a good thing to, let's look at that. Distance traveled since time 0. So we would integrate 0 to t of r omega, and we use a d tau. The reason for that is just the t has a fixed but arbitrary meaning, and the integration variable can't be the same, you know? Otherwise it begs the question of which is t is which. Anyway, you do this integral, what you got? You got yourself an r omega tau evaluated from 0 to t, which of course is just r omega t. So in this case, the distance traveled is just time times r omega. So the speed for this path is constant, but the velocity is not, right? The velocity is changing, isn't it? See it? It's changing direction as time goes on. All right, so that's velocity. That's speed. What else is there? Distance traveled. We have to integrate the speed to find the distance traveled. What else is there? There is acceleration. So acceleration, A, is equal to the derivative of the velocity with respect to time. Acceleration is also a vector. So position is a vector, velocity is a vector, and now acceleration is a vector. You could also, of course, talk about average velocity. What would you do if you wanted to talk about, excuse me, my bad. You could talk about average acceleration, right? You'd do like velocity at time 1, subtracted from velocity at time 2, and divide by the duration. That would give you average acceleration. If you wanted to, you could talk about that. But usually our default is to talk about the instantaneous acceleration, which is the derivative of velocity. Now let's calculate it for our example. For example 1, what is it? So we've got d dt of minus r omega sine omega t, d dt of r omega cosine omega t. And let's see here. So when differentiate sine, we get cosine. The chain rule pulls out another omega. And so what you got here is a minus r omega squared cosine omega t, and then minus r omega squared sine omega t. In other words, minus r omega squared times cosine omega t, and I seem to have dropped my 0, didn't I? That's bad. My apologies. There's a 0 here in there. Sorry. I'm not trying to neglect the third dimension. I'll put it back in there. And this one is simple enough that I can plot the position and the velocity and the acceleration by time. I can make a picture of it for you guys. As you guys were suggesting, it's really in the plane z equals to z naught. All right, so if this is the z-axis, man, here's my x-axis, my y-axis. What we're dealing with here actually is a circle. The radius of the circle is r, all right? And what's going on here is if I was to say, look at this here, is my, oh, my bad. Sorry, guys. My position would be like this, right? My position vector from the origin up to there, like that. And the way to visualize the velocity is as if it's attached to the trajectory, right? Like you should visualize the velocity as pointing in the direction in which you're going. So the velocity here, assuming that the rotation is this way, and I think it is if you study it. So the velocity is something like this, right? I'm sorry, let me try it over here. There's the velocity is like this. Over here, it's like this, okay? My picture is not great. Let me try that again. So it's challenging for me to draw 3 dimensions on the board sometimes, but like that. The velocity should be tangent to the curve, and it points in the direction in which you're going. The acceleration, on the other hand, what's it look like? Outward, yeah.
Is trajectory always based on the origin, or?
The position is based on the origin, yeah.
Or sorry, my bad, it would be inward.
Inward towards the, right? So it doesn't have any vertical part, right? It's just a horizontal vector. And you're right, it's pointing inward, so it's like this, right? Over here it's like that. So the acceleration points to the center of the circle. And it points directly towards the center of the circle because in this particular case, we're looking at constant speed circular motion. Constant speed circular motion, the acceleration, it turns out, is directly center seeking. All right? Now, in general, circular motion doesn't quite work that way. Like, there can be another part of the acceleration for circular motion which is in the tangential direction. All right? We'll talk more about that some other day. That's not really what we're after today. Let me give you some more examples here. So let's do example, let's see here, 2. I'll try to make this one a little bit easier. Suppose we had r of t was equal to, let's say, alpha t, beta t squared, gamma t cubed, all right? Alpha, beta, and gamma are dimensional constants. I need to put them there, technically speaking, so that I can give this actual units of like meters, right? Because if you think about it, in order for like alpha t to have units of meters, if t is in seconds, I need alpha to be what? Like a meter per second, right? If position should have units of meters, all right? So like, if my beta t squared is going to have units of meters, well, if a t is like a second squared, the beta is going to have like a meters per second squared type unit, right? So we can think about alpha, beta, and gamma as being constants which have the appropriate units in them to make this consistently, like dimensionally consistent, every component having the units of meters, because position should have meters, velocity should have like meters per second, acceleration should have like meters per second squared for each component of the vector. Now, anyway, let's just do it. What's the velocity? So we just differentiate component-wise. We get alpha, 2 beta t, 3 gamma t squared. There you go. What's the formula for the distance traveled by this path from time 0 to time t? Distance traveled from t equals 0 to t. So integral from 0 to t of the square root of alpha squared plus 2 beta tau quantity squared plus 3 gamma tau squared quantity squared. Close that square root, d tau. So you guys have been in calculus 2, like, you know, what, a week? So you know how to integrate this. I'm joking. You'll never learn how to integrate that. It's impossible. So relax. Yeah,
but I don't think I can do that.
No, I don't think we ever learn how to do that in calculus 3. Certainly not for arbitrary constants alpha, beta, gamma. However, if I gave you numerical values for alpha, beta, and gamma, you could easily put this into a computer and calculate it, right? So there's a straightforward path to actually calculating the distance traveled if I was to give you a specific choice of alpha, beta, gamma, right? And so, you know, one of the questions that I ask in here is find a formula for the distance up to an integral. If I ask that question, this is the answer. All right? So you just have to find the speed and integrate it. All right? What's the acceleration here? Yeah, 0, 2 beta, and we got a 6 gamma t. So there you go. That would be the acceleration at time t. So the deal here is pretty much the same in 3 dimensions as it is in 2 dimensions. All right, like you just have 2 components rather than 3. All right. So let us take a step back, though. Since many of you have never had physics before, it's kind of, in some sense, rude to do this to you. But we should also talk about the one case which is kind of quirky. And allows us to not use vectors, which is one-dimensional motion, right? One-dimensional motion is the thing you probably have studied in like Calculus 1 already, at least a little bit, you know? Depending on how much your professor hated physics or not. So I don't know, it is a standard topic for Calc 1, but it doesn't always sort of get much airtime. But one-dimensional motion is special because we don't really need vectors. So there are some special conventions at play in one dimension. Basically, in one dimension, we use the sign, plus or minus, to indicate direction, all right? And so there's no, you know, the speed is just the magnitude of the velocity in one dimension. All right, so like, to calculate distance traveled for a one-dimensional problem, you just have to integrate the absolute value of the velocity over the time. So let's look a little bit at this. One-dimensional motion. And so in one-dimensional motion, the question is like, what kind of one-dimensional motion are we talking about? Are we talking about like horizontal motion? Are we talking about vertical motion, right? You know, what kind? So let's just, for the sake of specificity, let's use x for the moment. If it's, you know, motion in x, let's talk about that. Then that makes x of t position. That makes v, which is dx dt, velocity, right? And then the acceleration is dv dt. There you go. In this case, the speed, we don't have a special symbol for it, but the speed is the magnitude, like the absolute value of the velocity. It's kind of annoying to me because this is incongruous with our notation for speed in 2 or 3 dimensions. It's just what it is. There's some things like this in physics we just can't fix notationally. So if this was one-dimensional motion in x, this is what we mean by position, velocity, acceleration, right? If you're talking about motion in y, what would that mean? One-dimensional motion in y, what would that be? Up and down, right? You have y of t. Your velocity then would be dy dt, right? And your acceleration would be, well, d squared y dt squared if you like. But again, it's dv dt. Right. So yeah, let's be a little bit more specific here. What's a good example of one-dimensional motion? How about this? Take this marker, right? And I do what? I throw it up and come back down, right? Why did it come back down? What's going on there? Gravity, right? So example 3. We could start with gravity. So what's gravity say? It says the acceleration, right, is equal to minus g. Now, it's a custom in here to let g be equal to 9.8 meters per second squared. Now, that's a pretty good approximation to the gravitational acceleration near the surface of the Earth. It varies about plus or minus 0.1 of that, but we just take it to be 9.8. I'm very tempted just to make it 10 to make calculations easier, but I mustn't. It's not 10. So there is that. So if that's the case, then how do you find the velocity? See, we've got minus g is equal to dv dt. So how do I find the velocity then? Take the antiderivative. Very good. So like v at time t, right, is going to be equal to some constant, right, minus gt. What's that constant though? Let's think about it. So let's put in like time 0. v of 0 is c minus g times 0, right? So therefore, v of 0, which we're just going to call v naught for the sake of, you know, a nicer notation, is v of c. So in other words, in short, we find that v is v naught minus gt. So there you go. That's the velocity at time t if we're dealing with constant acceleration due to gravity. Now, of course, this is what? This is equal to dy dt, right? So what can we do? Well, we can anti-differentiate again, or integrate again if you like. And we get y is equal to c2 plus v naught t minus 1/2 gt squared. But what happens if you look at time t equals to 0, what do you get? C2 is going to be y of 0, right? If you plug in time 0, the terms of time drop out and you're just left with that constant that we had to add from the anti-differentiation. So lo and behold, the formula is y naught plus v naught t minus 1/2 gt squared. And there you go. That's the formula for position as a function of time. All right? Are there other formulas we know for one-dimensional motion with respect to gravity? What do you think, guys? I mean, already you could solve a multitude of problems with these two formulas alone, right? These solve many, many things. For example, let's see here. All right, here's a question. Think about this, right? Oh man. Well, imagine that I caught it. All right. How high did the marker go? Let's say it was about my height, right? Away from where it left the marker to the top of the trajectory, right? It's about my height. And let's pretend my height's 2 meters. Let's pretend. So if the marker leaves my hand, going to my actual height of 2 meters, how fast did the marker leave my hand?
V naught.
Yeah, how fast? Give me the speed, the actual velocity. Figure it out. So here's a picture. I'll add a top hat, as is my custom. So you got your marker, all right? So this distance, 2 meters, is its height. That's the maximum height that the marker went to. How fast did I throw the marker with? What was its initial velocity?
0.
It was not 0. I mean, before it left my hand, sure, but like it's 0 right now. But what I'm talking about is right before it pops off my hand, what is that velocity that it has in its initial flight upward, assuming it goes to a max height of 2 meters? Is it the same velocity when it comes back down? It is, but that's another story. My question is just, what is this? So let's think about it. At the top, we have 2 meters, right? So what happens at the top of the flight? Velocity equals 0. So how much time does it take? All right, so we've got 0 is equal to v naught minus gt. Right? So that's the time to the top, apparently. Let's see here, what else do we know? Actually, I think given our current technology, this problem's kind of a pain. So the time to the top would be, the v naught we don't know, right? Divided by g, which we do know. Great. And what else do we know? We know that the y at the top is what? So y minus y naught, that's the change in y, right? The change in y is, and the two events I'm thinking about are the event of the marker leaving my hand, right? And when the marker is at the very top of the flight, which is 2 meters up, right? So the displacement in the y is 2 meters. We're assuming that, all right? Because that's my real height. So 2 meters. Now, what else do we know? V naught t, so y minus y naught is v naught t, right? Minus 1/2, minus 1/2 gt squared. But we also know what? We know that t, the time we're not really interested in, is equal to V naught, which we are interested, over G. So what I got myself is 2 meters, V naught times V naught over G minus 1/2 G V naught over G squared. Plugging it in. And we can solve this for V naught, right? So we got here, we got 2 meters is equal to V naught squared divided by 2G, actually. Because the G's, they'd be canceling, and 1 minus 1/2 is 1/2, right? So, yeah. And so, lo and behold, the speed the marker left my hand with is apparently the square root of 2 meters times 2 gravities, 2 G's, which is 9.8 meters per second squared. Notice how the units work out. We get a meters times a meters, which is a meter squared. We get divide by second squared. Square root of meters squared per second squared is meters per second. Hooray. So, yeah, whatever that works out to. I need a calculator. Square root of that thing. I get, I think I get 6.261 meters per second if I didn't make some kind of silly calculational mistake. Right? And if you guys could remember the calculations we did last week, maybe you could convert that to miles per hour, right? What is it? What did we figure out last week in terms of miles per hour versus meters per second? What was the conversion? You don't remember? Well, I don't either, so you'll have to look it up. Okay. Now, there's more to say here. In one dimension, there's kind of slick formulas that you can find. Let me talk to you a little bit about those while we're at it. So for 2 or 3 dimensional motion, it's not possible to write the position. It would not usually be possible to write the position as a function of velocity. But here, when we're just talking about 1-dimensional motion, it may make sense to talk about position as also a function of velocity. So let me show you how that goes. So we have acceleration is dv dt, all right? But a trick you can make in this case is to trade that for dy dt times dv dy. This is basically just the chain rule. But what is dy dt? What's that? Okay, true, but we have another name. No. Easier. What is dy dt? Is velocity, right. So what we have here is, instead of having a is dv dt, we have a is v dv dy, which gives me joy to say. So v dv dy, which is wonderful, because something you'll learn soon, and I can tell you now. Now, if this acceleration is a constant, right? Like, let's suppose it's minus g, as we just were. So you got minus g times dy is equal to v dv. In other words, think of dy as like a little infinitesimal change in y, multiply it to the other side, and then integrate both sides. And when we integrate, we have to mind the u substitution, which means this one has to go from y0 to yf, and here initial velocity to final velocity. In so doing, we get minus g times yf minus y naught is equal to 1/2 vf squared minus v naught squared. And let me rewrite this in a more useful form for us. Vf squared is equal to v naught squared plus, in this case, minus 2g yf minus y naught. This is a wonderful equation, which we call the timeless equation. Do you see why we call it the timeless equation? It's got no time. It's not especially exciting, the reason for it. But if you knew the timeless equation, you see we could have solved this example even easier, right? Because you can just apply this formula to the example at hand. You know the change in, you know that yf minus y naught is 6 meters, is 2 meters, my real height. And you know that Vf is 0 because of common sense. It's the top of the flight, right? And so you can easily solve this equation for V naught. Yeah? 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 All right. Now, but don't let this derivation just apply to the constant acceleration case, right? If we had, a formula for the acceleration which somehow depended on velocity, we could integrate that formula to find velocity as a function of position. We'll do that on occasion. So it's just kind of a very special one-dimensional trick that I should share with you, and now I've shared it. So there it is. Now, let me show you a couple of examples here with the projector, if I can get it working. So you guys have any questions about the class while I'm fussing with this silly computer?
Yeah.
Go for it.
So with, like, you have a lot of different, like, resources for us to use, like, with, like, in-class lectures and the lectures that are online, and then the book itself. When it comes to, like, our quizzes and exams and stuff, is it mostly based off class and everything else is, like, at our discretion to, like, understand better, or, like, is it all free game for?
What matters most? Order of operations. All right, so what I say in class, of course, matters, obviously. What is in your homework matters a lot. What is in these notes, these typed new notes I made just for you guys, it matters, right? And then after that, everything else is just supplemental. Okay. Yeah.
Okay. So it's like
Because I do have like 3 years of lectures posted. I don't expect you to watch all those. Okay. Nor do I expect you to read the book, because, the book has yet another system of notation. Please use the notation I use in class, and this is why I'm writing these notes, so you have a record of how things are done in here. Does that help? Yeah. Do not. I'm trying to make it easier. Like, you really can just focus on the homework in here, taking notes in here, understanding what we do in here. You should be good. Like, the reason I've linked those older versions of the class is just in case you need more examples. There's never enough time in physics to do the examples that constitute all the possible examples you can see on the exam. We have to operate by concept in here, not by mimicry. Like, mimicry won't do it. You cannot memorize all the problem types in here. It's just impossible. I could do it in Calc 1. We also have a lot more time to teach that. Here, there's just not time. Speaking of time, let's go on. So here's an example. I have a sailboat, begins at the island of Cats, makes a displacement of 20 miles at 20 degrees south of east. The boat changes course to 30 miles, 30 degrees south of west, and then finally travels 10 miles due north where it reaches the island of Dogs. In what direction should the boat set sail in order to return to the dreadful island of Cats? How far is the island of Dogs from the island of Cats? Please express the direction in terms of standard angle. So the way I solve this problem is to, basically convert the given angular information into convenient unit vectors that express the direction. So like 20 degrees south of east tells me a standard angle of minus 20. So I put that into my handy dandy unit vector, and that gives me the displacement of the first leg of the journey. All right, the displacement. Change in position. Now, then the second one was at 30 degrees south of west, which would correspond to a standard angle of 210 degrees. And so I do, cosine 210, sine 210 times 30 miles, which gives me that displacement vector right there. I need my lasers. I had lasers to point at stuff. I've lost my lasers. It's so sad. This will have to do. So that's my second displacement. Then the third displacement was due north. Well, due north is easier, 0, 10, right? no trigonometry needed there. And then what's the net displacement? The net displacement would be, you know, the first displacement plus the second plus the third. But I think here, oh my bad. So if delta r denotes the displacement necessary to get back where you started, then that would mean that the sum of this displacements is 0, right? If you go back where you started, the final displacement that we are not given but we're trying to find must be the one which adds to 0 because we're back where we started. And then I just do algebra. I solve for the delta r I don't know, and I get that. And after that, it's, you know, the vector stuff we were doing last week, right? Like magnitude, angle, all that jazz. Here's a picture of it, right? So I hope what we're doing right now brings new life into the vector things we were doing last week, right? Which were just kind of more formal mathematics. This example right here, I have a question about a mouse creeping along like it's a mouse creeping along a floor. It goes to here, it goes to here, climbs up something, and then it wants to shoot a laser back to here. The question is like, what angle does it need to shoot the laser above the horizontal? And so like I just, what I do is I calculate the displacement, add them together. That gives me the point where the mouse is at D. And then I simply take, you know, A minus D to get the, or D minus A, I forget which one. You know, I get the vector from here to here, the displacement vector from here to here, and then I measure the angle off the z-axis to find like the angle I should shoot the laser at. So this is the kind of thing that we can use vectors to do, and in conjunction with this notion of displacement, I think it becomes interesting. Now I have tons of examples in here, and I won't cover them all in class, but maybe we'll do some more next time. I'll at least talk through them with you guys. But I think that's it for today. So thank you for your patience.